In this video, we're going to start taking a look at one of the most important concepts of differential calculus, and that's going to be optimization and applied problems. And the good news is a lot of this isn't really anything new, considering that we've already taken a look at being able to optimize the graphs of functions. But we are going to learn about how to be able to work with a number of different terms, such as maximums, minimums, things that we've already seen, but also with preliminary and secondary equations, this thing called a feasible region, and also some new techniques for being able to solve these applied problems. And just as an example, let's say for some reason we're given that we want to try to build a fence, and let's say for some reason we have the total amount of wire that we have. So we have a wire fence, and maybe the total amount of wire that we have is, let's say, 300 inches or something like that. All right, so we're not really building a big fence, maybe for a garden or something like that. And let's say we want to maximize the area. Okay, well, we know that we can just go ahead and use the perimeter. And for that, we could just go ahead and try to maximize the area. So if we have a length times a width, the maximum would be xy of this. All right, so that's the types of things we're going to be looking at. Okay, or maybe the other way around. Let's say for some reason we need to build a fence that's maybe 30 inches square in the area. And what we're doing is we're looking to try to figure out what's the minimum amount. Okay, so we have an area that's equal to 30 square inches, and we want to minimize the perimeter. Right? So those are the typical types of problems that we're going to be looking at in this section. Now, we have this thing called the preliminary equation. The preliminary equation is what we're trying to optimize. Okay, so the preliminary equation is essentially what we are trying to maximize or minimize. Okay, so in the given example that we had maximum equals xy, or we know that the perimeter, if we were to take a look at this, if we were trying to minimize our perimeter, that would be 2x plus 2y. Right? So both of those would be the preliminary equations. Okay, so this is a preliminary right here, and this is a preliminary right here. Now we also have these equations called secondary equations. And the secondary equations are essentially the ones that are given to us. So we can figure out what's given already. So for instance, one preliminary equation that we were looking at before with respect to the very first example was trying to take the wire and trying to say it's 300 inches, and we want to try to optimize that. So we could say something to the effect of 2x plus 2y is equal to 300. All right, so that would be a secondary equation. And another one down here, we know that the area is 30 inches square, so xy would be equal to 30. Okay, so this would be a secondary equation, and this would be a secondary equation. All right. Now, the feasible region is going to be the possible values for x or for y. Okay, so, and most of the time what we're going to do is we're going to be able to solve in terms of either x or y and just get a singular equation in a singular variable. All right, we don't want to have two variables, otherwise then we're in Calc 3 and we have multivariable calculus, and that's not good. All right, so at this point, we're going to go ahead, and once we build up the equations, then we can go ahead and figure out what the techniques for solving are. All right, and our techniques for solving are going to be pretty easy. All right, so what we're going to do is we're first going to set up the preliminary and secondary equations. Once we do that, we are going to substitute the secondary equation into the preliminary equation. Next, we're going to find the feasible region. All right. And when I go through an example, I'll show you what the feasible region are. Again, feasible region is just the possible values for x. Then we're going to find the optimal values. Okay, so we're going to take the derivative of our preliminary equation, and we are going to solve. And then finally, we're going to use all of the above information to answer the actual question. All right, and we want to make sure that we're actually giving my math lab or the instructor exactly what they're asking for. So this first video, we're just going to show a very basic example of this, all right, just to kind of go through the steps. So what two non-negative real numbers have a sum of 54 and the largest possible product? All right, so first thing we have to do is we have to go through and set up the two equations. Okay, so what is it that we're trying to optimize? Well, we're trying to find the largest possible product of two numbers and two non-negative real numbers. So let's just call those numbers x and y. And so what we're going to say is that since we're trying to find the largest of those two, the maximum is going to be xy. Now, what is the secondary equation? All right, well, the secondary equation says that we have the sum of 45. So we can say x plus y is, or 54, excuse me, is equal to 54. Right? Or another way to write this by subtracting x from both sides is y is equal to 54 minus x. Right? So that's step one. Step two, let's substitute back in. Okay, so what we're going to do is we're going to take this value right here, 54 minus x, we're going to plug it in for y. So now we're going to get that the maximum is going to be equal to x times 54 minus x. Right. Next, we're going to find the feasible region. And the feasible region is pretty easy for this one. What we're going to do is we're going to take a look and we're just going to go ahead and say, okay, well, this is our first. And we just want to make sure that to get a maximum that these are non-negative values. All right, so the lowest possible number that we could probably put in here is 0. And again, we just want to make sure we get non-negative values out of this specific problem. So x, the lowest possible number we could have is 0. All right, and if I plug in 0, quite obviously, the maximum equation is going to be 0. And then 54 minus x, if we just set that 0, the highest possible value is going to be 54 for us. Think about if you plug in anything bigger than 54. Like let's say, for instance, x was equal to 56. Well, that means we would get 56 times 54 minus 56, 56 times negative 2. And clearly that's going to be something like negative 112. And that doesn't make any sense. We don't want a negative value to get our maximum. Right? So that's how we determine our feasible region. We just go through, and usually we could just set the maximum equal to 0 and solve for the different zeros of that maximum. Next, now we're going to take the derivative of the maximum function. Now, another way to write the max function is going to be by distributing the x, and we could write that as 54x minus x squared. I'm going to take the derivative. I'm going to call it d max dx. And the derivative is really easy. 54 minus 2x. We're going to set that equal to 0. Right? So remember, these are the critical values. And critical values are very important. They tell us the points of inflection. They tell us maximums and minimums of graphs. And we know that this is going to be a quadratic with a parabola that's concave down. So if we were to graph it, and this is not a good picture at all, but it would probably look something like this. And we're trying to find this maximum point. All right, if you really want to go in your calculator and graph it, it should pass through the origin, by the way. I know that's not a really good graph. But regardless, we know that we can just add 2x to both sides. And then we can divide by 2. And we can get that 27 is equal to x. And that's certainly within the feasible region. Okay, so that's why we have that feasible region, is to make sure that the answer makes sense. However, we haven't answered the question. Let's go back. So this is step 4, and now we just need step 5. All right, so we know that x is equal to 27. Question says find two non-negative real numbers. We found one. How do we get the other? Well, remember that y was equal to 54 minus x. All right, so we're just going to go back down. And since y is equal to 54 minus x, which is the same as 54 minus 27, just by substitution, we know that y is going to be 27 as well, since 54 minus 27 is 27. All right, so that's our two numbers. Nice and easy. All right. Now, on a scale of 1 to 10, this is about a 1, okay, maybe a 1.5 because I picked a little bit bigger numbers. All right, but the goal is to illustrate how to work through these problems, okay? And that's what we're going to do in the remainder of this section. We're going to work through a bunch of optimization problems just to see how to go through the techniques to be able to solve these types of optimization problems, especially with the calculus and algebra.